All right, class, we're going to look at design process, in particular how it applies to our class, IED, and Principles of Applied Engineering. What is design? What is it? What is a design process? Design process examples, and design process used in POE, IED, and Principles of Applied Engineering. Where design is often used as a generic term that refers to anything that was made by a conscious human effort. Design is also a process that is used to systematically solve problems, specifically engineering problems. So this entire presentation is going to go off the process that we used in my robotics team last year. Went to the World Championship. So what is a design process? The design process is a systematic problem-solving strategy with criteria and constraints used to develop many possible solutions to solve and satisfy human needs or wants, and to narrow down the possible solutions to one final choice. This is an example of a engineering design process by NASA, and it deals with rocketry, and this goes back to, was that 1962? So they have steps I went through that fully described the different aspects of the rocket, and fully documented, and they come up with their final product. And if it has flaws, they go back and they look at their design process and figure out where they can make improvements. So it's all right. Here's one example, design process example, 9 steps. Identify problems and opportunities, frame the design, investigate and research, generate alternative solutions, choose a solution, develop work, model, prototype, test, evaluate, redesign. With robotics, what we do is we build a working prototype, either out of wood or cardboard, and it fits certain constraints, like an 18 by 18 by 18 robot. That then we take it through the steps. Similar pattern here. We identify, define, explore, generate, choose a solution, develop, model, prototype, test, evaluate, redesign, improve, and then you continue to go through that. Like with a robotics competition season, you're always redesigning. Here's another one. Define the problem, brainstorm, research, and generate ideas. So you can see there's a pattern that goes here. Identify, explore possibilities, select your approach, develop and design, and make a model, test, evaluate, refine, create, communicate. So with IED and Principles of Applied Engineering, we're going to kind of consolidate some of those into 6 steps. But then within those 6 steps, you're going to have several teams that are applying their knowledge and skill toward subsystems, which is a drivetrain, lift mechanism, robotic arm, power, stuff like that. So here's our steps. Define the problem, generate concepts, develop a solution, construct and test a prototype, evaluate the solution, present the solution. So in our robotics season, we go through the first 5 steps pretty quick, or 4 steps pretty quick, and we're developing that prototype within a couple days. Design the process in POE, Principles of Engineering. An example of one design process. Many design processes exist and are just as effective. Some are more complex. We break it down into a half dozen steps. And if you consistently use the same process, you can't just change the concept of your process halfway through, let's say, a robotics season. You have to follow the same process so you can get dependable results when you make those changes. All right, so identify the problem. Under the define problem, step 1, identify, validate the problem, who says it's a problem, needs and wants, prior solutions. It's kind of important that who says it's the problem. Let's say that you have someone that's in charge of the robotic arm, and they say the drivetrain is a problem. Do they have a legitimate complaint about the drivetrain if their subsystem was the arm? Was there prior solutions? A lot of times robotics teams will share ideas and solutions. that they solved before, and so that kind of speeds up your robotic season. Justify the problem. Is the problem worth solving? Um, can your robot score points? Can it defend? If yes to those, then you've got a nice robot. Should you solve it? Are you going to take away from the ability to be competitive if you solve one problem? It could create two other problems. All right. Create design requirements, specifications, criteria, and constraints. Criteria is usually something you come up with before you start the project. Constraints are things that you kind of develop as you go along. You can have some constraints at the beginning, like budget, time, but you're going to see that as you, in this case, build a robot, you're going to come up with constraints during the build process. Like if you want to put batteries in one spot when a robot arm's supposed to go there, you've got constraints, and you're not going to come across that until you actually start building the robot. So design brief. Written plan that identifies problem to be solved, its criteria and constraints. Used to encourage thinking of all aspects of the problem before attempting a solution. Before you attempt the solution, you have to brainstorm, and that actually will bring costs down because it's okay, well, let's say putting a new motor on is going to cost you $200. Well, if you can solve it some other way, say put gears on your existing motors and put chains in there that drive those gears, you can actually save money. So brainstorming can help you get around constraints. So research, brainstorm possible solutions, define the problem. Problem valid and justifiable? No. Then you go back and redefine the problem. Yes, you generate concepts. So once you get to the step 2, that's where the exciting part goes. That's where you start putting gears on and wheels on and batteries and wiring things up, and you develop those concepts in AutoCAD. I mean, you got Autodesk Inventor, Onshape, Fusion 360, SolidWorks. You develop electronic concepts as well as physical concepts. Consider the additional design goals. Apply STEM principles, science, technology, engineering, math. Especially the math part. The technology, in the case of the robot, is the physical hardware. Engineering is the people. The math is the thinking and sketching. Select an approach. By using this process, you can select approach, and if it doesn't work, you can come back and figure out, okay, what step did we break down on? So decision matrix, you want to look at cost, complexity, development time, skill level. Let's say everyone on the team is rookies. Your development time is going to have to increase, which is going to increase your cost and complexity. So you have to look at, let's say you have 6 teams and they're all working on a different part of the robot: drivetrain, power, electrical, pneumatic, lifting mechanisms, stuff like that, scoring mechanisms. So you have to look at, you want a robot that can score points, or do you want a robot that can be a good defender? It all depends on what you want, what your goals are, and what your time constraints and budget and the cost. It's like with a robot, there may be some parts where you have to order and it takes 3 weeks. Well, your build season is over in 6. So if it takes you 3 weeks to get that part, is it cost effective to wait around to put that part on a robot when you could be developing ideas for other stuff? So generate concepts. Needed technology exists? Yes. If the technology necessary to develop the solution does not exist, scientific research may be necessary to pursue a solution. So if you don't have the technology, in this case, let's say you don't have a backup control hub, which would be your technology that controls the flow of information going from your computer to your robot. You may have to develop other solutions, cut back on motors or whatever. Let's say you do have that control hub and you can add on the extra wires and motors. You develop a solution off that. Scientific research needed. Let's say you have to go back. How far do you go back to find a new problem? Instead of a robot that can score, you're going to design a robot that can defend. All right, justify the solution path. You have to justify it by, let's say, okay, well, we can't get the parts, so we have to come up with a different plan. Technical drawings, that would be your Autodesk Inventor, Fusion 360, SolidWorks, Onshape. Gives you technical information to produce a product. I've seen teams go all the way to the World Championship just off their engineering notebook, and the robot couldn't score anything, but they had a great engineering notebook, and they actually went to the World Championship just based off that. So if a solution is found to be invalid or cannot be justified, a designer must return to a previous step in the design process. This is where your coach kind of decides where you want to go back, how far you got to go back. Either all the way to generate new concepts or redefine the problem. And we get to step 4, construct and test the prototype. The way you kind of speed this whole process up, like with robotics, you build and construct a prototype out of cardboard or plywood, and you mess with that cheap prototype. Like our constraints was our robot had to be 18 by 18 by 18 inches, 18 tall, 18 long, 18 wide. So we just built a box that had some wood gears on it, and we took it through this process over and over again until we got a robot that could score and defend. We could fit the batteries on there and all that kind of stuff. So that's just another way you can speed up the process. Test the report. Test in this case would be driving the robot on the robot course and scoring points and meeting with other teams that you're competing with and against. In the case of the robotics, you can be allies in one competition and adversaries in the next. So the benefit is to train together. And so, if a testable prototype cannot be built or test analysis indicates a flawed design, the designer must return to the previous step of the design process. Let's say the first competition, your robot didn't do very well, so you have to go back, generate a new concept or redefine the problem, develop a solution. So you may have to go back, evaluate solution effectiveness, reflect on design. So let's say you make it all the way to the very end and going into the World Championship, and you want to reflect on your design and make some changes. Like let's say your batteries are running out, and so you want to throw another battery on there. Well, you have to take it through there and show that you're under the certain weight and all that kind of stuff. There's certain constraints that you have to comply to. Optimize, redesign, return to prior design process steps necessary, revise design documents, which would be the AutoCAD designs. Then we say, okay, we got a robot that we like. It does well in competitions. So we evaluate, and solution solves a problem. The problem would be, say, hey, we want a robot that can score points, be competitive. And so yes, it does compete and it does score points. So we present the solution, i.e. the robot, we take it to the competition and we compete. And so if we did all these steps, we should be able to build something that can be competitive. And you can use that in any aspect of your life or your career. And if you're designing a power grid for a petroleum plant or something like that, you take it through these steps. You have to document, communicate your project, formal presentation. You have a boss that you have to answer to, and they're going to ask, okay, well, communicate your steps you went through. And so then you can give confidence to the people before you flip that switch on that the thing is going to do what it needs to do that you said it was going to do when you define the problem. And so you go through many iterations Many designs. In our case, we redesigned the robot lots of times throughout the season. Um, we didn't veer too far off. We want to make sure we score points and we can defend against the other team. So we didn't veer too far off. We didn't want to make too many drastic changes, but we went through many iterations. So the design product process, it's a product improvement or redesign will require the designer to repeat the design process, and it's a learning process, but it's a structured process that we follow, and we cut it down to a half dozen, 6 steps, and that's it. All right, so that wraps up this design process presentation. Look forward to our Zoom meetings and we can talk about this. And I'll see you in the next meeting or tutorial. And product innovation, improvement. All right, see you guys later.